All right, welcome to our second lesson on momentum. Okay, it looks like this. Okay, it's lesson 7, and it's conservation momentum. Now, yesterday we looked at Newton's second law, and we sort of rearranged Newton's second law to, instead of thinking of it as a net force causing an acceleration, we were able to think of it as an impulse causing a change in momentum. Well, this time we're going to look at Newton's third law. So let's say you have two cars. Right? Car 1, bam, car 2, bam, and they collide. Well, we know from Newton's third law that the force, the net force that car 2 puts on 1 is equal and opposite to the net force 1 puts on 2. Okay. All right, well, let's look at that. Now, this is the only force acting on it. So let's look at this as Newton's second law. So we'll throw that in. The force that 2 acts on 1 is going to be the mass of the first one times the acceleration of the first one, which equals the mass of the second one times the acceleration of the second one, negative. Now we'll do what we did yesterday, and we'll change acceleration to be a change in velocity over time. So let's write m1 times delta v1 over delta t1 equals minus m2 delta v2 over delta t2. Now, even though I've written delta t1 and delta t2, the time that car 1 is in a collision with car 2 for is the same as the time that car 2 is in a collision with car 1 for. It's the same collision. So I can just think of that as just delta t, and therefore multiply both sides by delta t and completely cancel it out. So this is what we're left with. Now let's expand this a bit, because this is change in velocity. So m1 times final minus initial equals minus m2 times final minus initial. And now I'll just distribute. So we have m1 v1 prime minus m1 v1 equals minus m2 v2 prime plus m2 v2. So now what I can do is I can bring all the primes together on one side and all the non-primes together on the other, and you get m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime. And I ordered it in that way for a reason. This, you'll notice, is the momentum of object 1 before the collision plus the momentum of object 2 before the collision. So it's the total momentum of our system, which is the two cars, before the collision. And then after, we have the momentum of object 1 after the collision, plus momentum of object 2 after the collision. So this is the total momentum of our system after collision. And we'll notice they're equal. This is called the conservation of momentum, where momentum is conserved in any collision. Now, of course, after the collision, the cars will experience other forces, like, say, take one car, it might be skidding off on the road, and that frictional force will bring it to a stop. But even in that case, right, as a car is skidding on the road, you have action and reaction forces. Remember, Newton's third law says every force comes in a pair. Right? And because every force comes in a pair, if you analyze that pair, their momentums will always be equal before and after. So in the case of friction, a car is being slowly pulled to a stop due to the road. Well, technically, depending on what direction that is in, the car would either be slowing down or speeding up the rotation of the Earth. But because the mass of the Earth is so bad, it's the actual change in velocity of rotational velocity of the Earth is going to be really small, right? And completely immeasurable, but not zero, right? Momentum is always conserved. So let's use this concept to try a couple questions. First question on the back. says a 57 kilogram factory worker takes a ride on a large, freely rolling 27 kilogram cart. The worker initially stands on the cart, and they both move at a speed of 3.2 meters per second relative to the floor. Okay. Then the worker walks on the cart in the same direction the cart is moving. So you can imagine just standing on a skateboard, and if you walk forward, you push the skateboard back. Momentum is going to be conserved, though. The worker's speed is now 3.8 meters per second relative to the floor, for the magnitude and direction of the final velocities of the cart. So based on this, would you expect the cart's velocity to increase or decrease? Well, due to conservation of momentum, it should decrease. If one increased, the other should decrease. But by how much? The same amount? No. Remember, momentum is not conservation of velocity, right? So it depends on their masses, and their masses are not the same. So we're going to have to calculate this. So conservation of momentum, total momentum before this interaction equals total momentum after the interaction. So before we have m1v1 plus m2v2, and after we have m1v1 prime plus m2v2 prime. Let's say 1 is the person and 2 is the cart. Now initially, v1 and v2 are the same because it says they're moving together. So I can even just write that as v. Right? But afterwards it's not. Now because this is a vector quantity, let's just have our positive direction as our forward direction because they don't give any specifics. Since everything's moving forward initially, we're just leaving it at that. So everything in this equation we know except for the final velocity of the cart, v2. So we're going to calculate for v2. We can make this side a little bit simpler by factoring out a velocity since they're the same, and then minus this term equals, and then divide by mass of the second object. And then you plug in all of your known values, right? And you should get 1.9 meters per second. Now it's a positive value, so that means the cart is still moving in the same direction. It's still moving forward, but since its initial value was 3.2 meters per second, it has clearly slowed down, which is what we predicted with conservation of momentum. Now let's look at the second question. The second question is a little bit tricky, right? Because I'm going to throw in energy conservation as well. We're going to use the two in hand, which is the great thing about physics. You can take one topic of physics and you should be able to apply it anywhere else. And that's what we're going to do. Now the tricky thing with energy, though, is it can be really, really hard in the real world to apply conservation of energy. Right? Especially in, say, for like collision reconstructions. Energy conservation, very hard to use. Even though it's still true, it's always true, it's so hard to use because energy is always lost to something. And it's always hard to figure out what is energy lost to. Usually you won't account for everything because you won't consider something. And you certainly won't be calculating everything. So energy can be very, very tricky, which is why you should always think of conservation of momentum before you think of conservation of energy. And I find the fact that we don't do momentum in grade 11, we do only energy, sort of forces kids to have a stronger framework with energy, and they tend to think of that first. So I will be putting a cool video, well, a 3-part video series, which is sort of like a video quiz that I found on YouTube, which is really good. So I want you to do that video and well, try the quiz and then see if you're right or not. It's fun, so enjoy. It's a cool experiment. All right, so this question we have two dynamics cart. That's just the carts that we use in the labs. That's what a dynamics cart is. Cart 1 has a mass of 1.8 kilograms and is moving with a velocity of 4.0 meters per second right. So let's draw this so we understand exactly what's going on, because it can be very wordy. So here's cart 1. It's moving to the right. Okay, with some momentum, I'll call P1. Along a frictionless track. Okay, so we're not going to consider friction. Dynamics cart 2 has a different mass and is moving to the left at a different speed. So we have dynamics cart 2 here, moving to the left with P2. Okay, completely different momentums. The carts collide in a head-on collision cushioned by a spring. So there's a spring here, right? And they collide, causing that spring to be compressed. Calculate the maximum compression in the spring. What? So they give you the spring constant, and we need to calculate how much that spring gets compressed from its equilibrium position. How are we going to do that? Come on. Well, we could do conservation of momentum. But we can also do conservation of energy. And you might want to lean towards energy because you might think, I learned about elastic potential energy. That's a half kx squared. And x is what I want to calculate. Why would I use this? There's no x in there. Well, all right. Let's think of it that way. Let's start with conservation of energy. See where that leads us. Okay. So before the collision, we have kinetic energy of cart 1, kinetic energy of cart 2. They're going in opposite directions, but for energies, for kinetic energies, they're scalars. We don't care what direction they're going in. So I'll just say this is a half m1 v1 squared plus a half m2 v2 squared. And that's it. Then they collide, right? And that spring gets compressed. Now at some point, you'll get maximum compression. But here's the question: at maximum compression, are the carts not moving? Does this happen? Answer: no. It could. That's a very, very special case. If the carts had the exact same momentum, then they would hit the spring, and the spring, which would apply equal and opposite forces on both of them, would cause them to accelerate at the exact same rate, and they would slow down, come to a stop, and then move apart. So in that case, yes, right? The two carts will have a velocity of 0 during maximum compression, but that's a very specific case. That's only in the case where the two carts started off with the exact same momentum, just in opposite directions. This is not the case. Our two carts have completely different momentums. So we cannot assume that they will be at a velocity of 0. We can't assume either one is going to be at a velocity of 0. So I'm going to have to write their kinetic energies here. So we'll have 1/2 m1 v1 prime squared plus a half m2 v2 prime squared, and then we do have a half kx squared for the compression in the spring. Now you can look at that and say, okay, what do I need to find? Well, I'm looking for x. Do I know everything else? Well, there's a half in every term, so you can make it a little simpler by multiplying every term by 2. Now I know the masses of everything. I know the spring constant of the spring. I know the initial velocities of the cart. These are what I don't know. I do not know the final velocity. One doesn't work. I do not know the final velocities of either cart. So I can't possibly solve this equation for x until I know v1 prime and v2 prime. How am I going to figure out the final velocities of the carts? Now we're going to come back to momentum conservation. That's where this is going to help us. Okay, but you might be saying, that's 2 unknowns. How's momentum conservation going to help us? Well, let's just start with this. Initially, we have m1 v1 You want to make a direction positive? Let's make left positive. Let's be rebels today and make left positive. So M1, V1, the first cart's moving to the right, so let's make that negative. Right? I'm pulling the direction out of the velocity term, so that's just its magnitude, and that's its direction. And then plus M2, V2 equals, so now what? We have M1, V1 prime plus M2, V2 prime. What direction are they moving in? I don't know yet. Let's think about what's actually happening. And these are two unknowns. How can I solve one equation for two unknowns? So we need to think a little bit deeper about this. Now we looked at the first scenario. Now the first scenario was if they have the exact same momentum, they come to a complete stop and then push out. But here's the interesting thing. What are their velocities when they come to a complete stop? 0. More importantly, the same. Now let's look at something where, let's say this one has a much greater momentum. If this one has a much greater momentum, it'll push more on the other one. So this will push more on the other one until this one starts moving back, before this one comes to a complete stop and then starts moving back. So when does the compression in the spring become the smallest? Let's do this in slow motion. So this one has the greater momentum, remember? So this one's going to be pushed back first. So they're coming in. This one comes to a stop. This one's coming towards it, and then this one pushes back. And then eventually this one's slowing down as this one's getting faster. And this happens. When are they at the closest point to each other? Are they at the closest point when this one starts turning around? Not necessarily, because as this one reaches 0 and starts to move back, which one had this one had the greater momentum, right? I can't remember. The video is like the opposite of what I'm doing. So this one has the greater momentum. So as they're moving towards each other and this one starts moving back, this one could still be moving at 5 meters per second and this one just starts moving back. So this one's still getting closer to this one. Eventually, right, this one will increase its velocity as this one decreases it, and they will reach the same velocity. Once they've reached the same velocity, that's when this one starts to overtake and this one slows down and they start moving further apart. So it's just like our initial case, right? They come, identical momentums, they come, slow down, and they reach maximum compression when their velocities are identical. It's the same situation, even in this one. Right? They will reach maximum compression when this occurs. So we can use that in our equation to say, okay, well, let's just not call it V1 and V2, let's just call it V prime. And let's solve for V prime. Okay, now I don't know what it is, so I'm just going to assume it's to the left, and if it turns out I'm getting a negative answer, I was wrong, it's to the right. Just solving for it anyways. And now we can actually factor it out. Okay? And we can divide both sides by that term. Okay. So if I divide both sides by this term, we get minus M1V1 plus M2V2 over M1 plus M2. That is equal to V prime. And if you do that, you will get 1.5 meters per second. It's positive, and since we put all of our directions in left for positive, that's our coordinate system, that means that spring will reach maximum compression when both velocities of the carts are equal to 1.5 meters per second to the left. This is great. Well, actually, I don't even need to know left, because I'm substituting into a scalar equation. So all I need is the 1.5. Not only that, but v1 and v2 are the same, so they're both 1.5. Now I know everything I need to know in this equation to solve for x. It's a little bit messy to rearrange, but you'll get x squared equal to, well, we have m1 v1 squared plus m2 v2 squared. This one I can factor out the v, bring it to the other side of the equation, so minus v prime times m1 plus m2. Okay, and then divide both sides by k. Okay. And then take the square root of it all. If you do that, you will get x to be equal to 0.035 meters or 3.5 centimeters. Now that's a challenging question because we use both momentum conservation and energy conservation, but using both actually helps to solve a lot of questions. Another example, just before I stop the video, I won't solve this example, but I tell you it, is called a ballistic pendulum. So you have a pendulum, and that pendulum can swing. And now if it has a certain velocity here, it has a certain amount of kinetic energy, right at the maximum height that's going to swing to, all of that kinetic energy gets converted to gravitational potential energy. So that's a great use of energy conservation. But now let's take this at rest and shoot it with a bullet. This is at rest, so it doesn't have any momentum. This has a lot of momentum. The bullet will hit it, get stuck in the side of it, and transfer that momentum to this object, which is the mass of both of them. You can use momentum conservation to figure out what the velocity of this is. Knowing the velocity of this, you can calculate its kinetic energy, which gets converted to gravitational potential. Now you could run this whole situation backwards. Let's say you had you're a CSI, and you have a gun. You need to know the velocity of the bullet that comes out of it. Well, you just take that gun, shoot your ballistic pendulum, measure the height that it goes to, and work backwards. You know the height, you know the kinetic energy. You know the kinetic energy, you know that final velocity in that momentum collision. You know that final velocity and the masses of everything. You can calculate using momentum conservation the initial velocity of the bullet. And that's called a ballistic pendulum. Alright, so lots of cool cases with that. But I'll stop the video for now, and tomorrow we will look at different types of collisions.